Hey guys, Mr. Hill here. Last time we talked together, we talked about exponential functions, and that's going to be the next focus of our class following our investigation to linear functions. I talked a little bit about some applications of exponential functions and how we recognize exponential functions from a table. But in order to proceed deeper into the conversation of exponential functions, there are certain ways of manipulating exponents and understanding how they mean that we need to be familiar with. So I want to do a brief review of some of those ideas. You may have seen some of these ideas in past years, so some of this may be old information for you, but some of it might also be new. So if we had an exponential expression like 2 cubed, that is a shorthand, of course, for understanding that the way we describe that is that that's the number 2 multiplied by itself 3 times. So we would see that as 2 times 2 times 2, which we know is 8. So this obviously, if we had x cubed, we would interpret that as x times x times x, but we don't really know what that means until we have a value for x. But that's how we would interpret what the expression x to the third power means. If we had something like 2 cubed times 2 squared, we understand that that's 3 2's multiplied together, also multiplied by 2 2's multiplied together, which is also 5 2's multiplied together, and that's 2 to the 5th. So one of our exponent rules, which you should remember from past years, is that one of our exponent rules that you should remember from past years is that 2 to the third times 2 squared is the same as 2 to the 3 plus 2, or 2 to the 5th. We can confirm this with the actual values. We know that 2 cubed is 8, and 2 squared is 4, and 8 times 4 is 32, which is also 2 to the 5th power. So how would we interpret something like 2 cubed squared? Now, somebody might quickly look at that and think that that should also be 2 to the 5th power. But let's look a little deeper. We know that the squared on the outside means we're really looking at 2 cubed times 2 cubed, and we just saw that that should equal 2 to the 3 plus 3, or 2 to the 6th power, right? So in this case, this is not correct. This is actually a multiplication of the power. So often we say a power raised to a power just involves multiplying exponents. So if I had x to the 10th raised to the 5th, whatever the value of x is, I know that should come out to x to the 50th power. So how would I interpret something like x to the 5th divided by x cubed? Well, if we write it out, that's 5x's multiplied together in the numerator and 3x's multiplied together in the denominator. We know that since all of this is multiplication, that we can divide out x's on the top and on the bottom until we have no superfluous x's remaining. Now everything is divided out on the bottom, and if everything's divided out, the only thing left is 1. And in the top, we have two x's multiplied together. So x to the fifth divided by x cubed has to be equal to x squared. How could we get the squared from the powers if we were doing this quickly? Well, we should note that that's x to the 5 minus 3. So it's the opposite rule, right? So a lot of times we might shorthand this rule So a lot of times we might shorthand these rules by saying that if we have x to the a times x to the b, that's equivalent to x to the a plus b. But if we have x to the a divided by x to the b, then that's equivalent to x to the a minus b. So here are the two main rules that you've probably seen in the past if you've looked at how to evaluate exponents. So the trouble with interpreting an exponent as it's the base multiplied by itself, however, this many times, is that that only really makes sense if your exponent is a whole number, or I should say a whole number greater than 1, because how would we interpret x to the first? We would have to say it's x multiplied by itself one time, which doesn't seem to make sense. To multiply, you need two things, so you can't multiply by something by just itself. But we just say that by default, anything raised to the first power is itself. So 2 to the first is 2, and 10 to the first is 10, and pi to the first is pi, because why not? So anytime you have something raised to the first power, that's pretty straightforward. But how would I interpret anything raised to the 0 power? This makes even less sense by the way we're interpreting exponents. Something raised multiplied by itself 0 times, that doesn't really make sense. What a lot of people often want to say here is that it just makes it itself, or that maybe it makes it 0, right? Well, we know that this shouldn't make any sense because we already said that to get a number to be itself, you need to raise it to the first power, not the 0 power. But what about this idea? This is usually the most common incorrect interpretation of what it means to raise something to the 0 power. So obviously what I'm saying is that's actually not correct. But what should it actually be? Well, a way to think about that would be, what if I had x to, let's say, the 5th power, I'm just picking a number arbitrarily, divided by x to the 5th power. What if I did this? Well, by one of the rules of exponents that we know, that's going to equal x to the 5 minus 5, which is also going to equal well, what's another way? So how could we find out what something raised to the 0 power equals? Well, there are a couple ways. One way that I like to do is to think of exponents as a pattern, right? So we've done this before, that let's say we had y equals 3. Let's say that we had y equals 3 to the x, and we had we started making a table here. And we know that when x is 1, y is 3. When x is 2, y is 9. When x is 3, y is 27. And we know this because we're following a pattern. Every time the domain, the x side, adds 1, the y multiplies by 3. This continues, this continues. But a lot of you we've used this trick before. What happens if we go backwards? If we extrapolate the pattern the other direction? On the left side, we would get that the exponent would be 0. But what would happen here? We would need something that when multiplies by 3 gives us 3. Well, the only thing that's going to work there is actually 1. So that means 3 to the 0 would have to actually come out to 1 in order to make the pattern work. Notice that that wouldn't matter whatever I actually put in as the base, right? If we had 2 to the x, if we did the same table but with 2, right? So now the pattern on the left is still plus 1, but the pattern on the right is times 2. If we extrapolate the pattern backwards, the result still has to be 1 if the exponent is 0. So it seems to imply here that raising something to the 0 power has to give me 1. Another way to show that anything to the 0 power has to be 1 is using exponent rules we already know. Let's say we had x to the 5th divided by x to the 5th. By one of the exponent rules we already know, we could shorthand what this should equal by subtracting the powers. So that means it would be x to the 5 minus 5, which is the same as x to the 0. So that's what we were talking about. But notice what we did here. We divided a quantity, x to the 5th, by itself. And we know that any time you divide something by itself, 10 divided by 10 or what have you, the result has to equal 1. So once again, we see that anything to the 0 power has to be 1. This is a major property of exponents, and it's something that you're going to need to remember because it comes up a lot. Whether we're graphing or simplifying, you do need to know that anything to the 0 power is going to come out to be 1, and it doesn't matter what the base is. This is one of the few times where what the base is actually irrelevant. So how about if I raise something to the 0 power? Let's say I had, so what if I raise something to a negative power though? What if I had like 3 to the negative 2? Like what does that even mean? Now the most common incorrect answer here is a student will say it's negative 9. And that is unfortunately wrong. The base here is a positive number, and you cannot raise a positive number to a real exponent and come out with a negative result. That actually does not work, and it can never happen. This is one of the ways to remember that you cannot interpret a negative exponent as making the result negative, because it just absolutely does not work. But then the most important question is, what would it actually equal? Well, one of the ways that we can show it is, just like we did before, look at extrapolating a pattern, right? So I use 3, so I'm going to make my table again. Okay, and I'll give myself a few more rows here. So, so this is what we've established so far. That if I raise it to the 0, I'm going to get 1. And then every time x goes up by 1, y multiplies by 3. Exponential situation, we have a geometric sequence on the right there. Okay, but let's keep going in the other direction. So if I go backwards now, if I would have to add 1 to negative 1 to get the 0, and again on this side there would have to be a multiplication by 3 to get 1. So thinking of it going backwards, I would be dividing by 3 to find the next result. Well, what do I get if I divide 1 by 3? Well, I get the fraction 1/3. What if I kept going backwards? Now what do I have to multiply by 3 to get 1/3? Well, the question is the same as dividing 1/3 by 3. So I keep dividing by 3, and that's going to give me 1/9. So take a look at what we have here. We have that 3 to the negative 1 is 1/3, and 3 to the negative 2 is 1/9. Another way you can notice what's going on here is that these are powers of 3, but they're just reciprocals. They're just fractions. So 3 to the negative 1 comes out to 1 over 3 to the first, whereas 3 to the negative 2 comes out to 1 over 3 squared. So it seems that raising a number to a negative power, let's say, I don't know what x is, but let's say I raise it to the negative 5, that can also be thought of as 1 over x to the 5th. So notice this actually has nothing to do with making the number negative, but it has to do with actually flipping the base. And for a lot of students, this is somewhat counterintuitive. It's not something that they would immediately think would happen. However, this is what a negative exponent means. So if I had 2 to the negative 4, I know that if I wanted to know what exact number that was, I know it's 1 over 2 to the 4th, which is the same as 1 over 16. So what would happen if I had, let's say, something like So what would happen if I had, say, something like 2/3 to the negative 3? Well, this actually means 1 over 2/3 cubed. Now that looks kind of difficult to interpret, so one thing that we could actually do it as instead is just take the reciprocal of the fraction being raised to the power. So I could think of that instead as 3/2 cubed. And then using my integer exponent rules, I know that that's equal to 3 cubed over 2 cubed, or 27. And then using my integer exponent rules, I know that that's actually 3 cubed over 2 cubed, which is the same as 27 over 8. So let's say you were tasked with simplifying this expression, and you were also told that you don't want the result to have any negative exponents in it. Now there are plenty of times in math where negative exponents are fine and we don't mind leaving them, but a lot of times right now you're going to be asked to simplify things such that there are no negative exponents left over. So if I had this situation, there's actually several ways you can do it. What some people like doing is actually just squaring everything inside the parentheses right away, and that's perfectly fine. You just have to remember how to apply all the rules correctly. So squaring the actually known integers, 3 squared would give us 9, and 2 squared would give us 4. So I'm going to start with that. For handling the x and the y, we're just going to use our exponent rules, knowing that x to the 5th squared, we multiply the exponents, that comes out to x to the 10th. Y to the negative 3 squared comes out to y to the negative 6. Now, if we were okay with negative exponents, this would be fine, but since we said we don't want any negative exponents in the final result, we have a y to the negative 6 here, and we want to redo that. Now, this literally means that on the bottom you have 1 over y to the 6th, if we wanted to write it that way, but that's going to put a fraction in your fraction, and that's not very convenient looking. So another way of doing is just knowing that if we take the reciprocal of something that's in the denominator, it's automatically going to put it in the numerator. In other words, everything else stays where it belongs, but the y to the 6th is now in the numerator, and note that the exponent is now positive because we did change its location from the numerator to the denominator to the numerator. If it were a negative exponent in the numerator, it would have ended up in the denominator. So let's say, for example, that was x to the negative 5, and that would make that x to the negative 10. Then that would be x to the negative 10 there, and that would move the x to the denominator in order to make the exponent positive. So that's how we could handle that.